Here we have the conservation of mass principle. You can see that this is very similar to the conservation of energy principle. The way that we write conservation of mass principle is total mass entering the control volume during delta t time minus total mass leaving the control volume during delta t time is equal to the net change of the mass within this control volume during that time period. We can write it like this: m in minus m out is equal to delta mcv, where delta mcv is equal to final mass of the control volume minus initial mass of the control volume. So this is the change of the mass of the control volume. If we want to write this in rate form, we can write it like this. These equations are called mass balance. Now let's consider the application of mass balance for a steady flow process. First, let's consider what is a steady flow process. So the idea of a steady flow is the flow rate does not change with time. Also, for a steady flow process, the mass inside the control volume does not change. Therefore, we can rewrite our energy balance equation that m dot in is equal to m dot out, because dmcv over dt is going to be 0. If it is a single stream, we can rewrite mass flow rates using density, velocity, and area as shown in this equation. If the fluid that we are using is incompressible, that is, if it doesn't change the specific volume when the pressure is changed, we can rewrite our mass balance as shown in here, where we dot our volumetric flow rates. However, you have to remember that there is no such thing as conservation of volume. However, when you are dealing with incompressible steady flow processes, it's easier to use mass balance equation in this form. Flow work and flow energy, both are same, is the energy or work that is required to push a mass of liquid into or out of the control volume. So here you can see that I have a control volume which has been connected to input and output tubes. So if you consider this volume of liquid in the inlet, the work that is required to push that liquid into the control volume is going to be flow work. So if you consider a piston and cylinder device like this, if there is no acceleration, the force on the piston is equal to pressure into area of the piston. And if you want to calculate the work done by this force by moving a L distance, you can calculate it by force into L distance. Because force is equal to pressure into area, flow work is going to be PAL. And we know AL, area into length traveled, is equal to volume displaced by the piston. So flow work is going to be equal to PV. In our previous lectures, we learned that the energy of a non-flowing fluid is equal to U, internal energy, plus V squared over 2, kinetic energy, plus GC, potential energy. If you are considering a non-flowing liquid, we have to add the flow energy to this. There is some energy that comes to the flowing liquid because of the internal energy, kinetic energy, and potential energy, and also flow energy should be there. So total flow energy of a flowing liquid is equal to PV, which is flow energy, plus U plus V squared over 2 plus GZ.